All right. Hi there. My name is Andrew Pachapluso, and I'm here with my partner, Ryan Lampy, and we are going to be discussing how we model vehicle depreciation using various numerical analysis methods. So our primary motivations for this topic is mainly because cars are a depreciating asset, and they depreciate so much so that a new car loses about 20% of its value in its first year. And typically after 5 years, a car will lose about 60% of its value. And since cars are such a massive purchase to most people, it's important to know just how much, be attentive to how much your car depreciates. The difficult part is that different makes and models can depreciate at different rates. So this can make it difficult to track or know exactly how much your car is going to depreciate. So we're going to, throughout this presentation, go over our various goals, which include modeling depreciation of cars using various numerical analysis techniques. And we're doing this such that we can help consumers understand how the value of their vehicle will change over time. And we also hope to help consumers determine if the sale price of their used car is fair. So our data source for this project is the Kaggle data repository. Kaggle is a very popular machine learning database for training models, and we happen to find data on there that meets our requirements. And our particular data set contains 1.23 million data points, and these data points were collected in September of 2017.
All right, and I will talk a little bit about the numerical analysis methods that we used. In our implementation, we wrote linear least squares, a polynomial least squares that uses quadratic least squares, as well as a linear piecewise interpolation. And in the implementation, we also used MATLAB's built-in cubic splines function just to kind of get a baseline and compare how its built-in methods are with our implementations. And we also have Neville's method implemented from an earlier assignment. One of the big challenges of this project was pre-processing the data. So as Anirudh mentioned, the data set that we had over 1 million records. And unfortunately, some of the data points were duplicates, or they had extra commas in their CSV format, and that caused a lot of problems parsing them. So I wrote a Python script to pre-process the data and remove some of those errors. I will demo this in a second, but kind of the basic usage of our implementation is that a user enters information about their vehicle on a PHP web page. That looks kind of like this. So you can see here where they enter the make, model, year, and then they would select the interpolation method they would like to use, as well as enter the mileage of their vehicle. So because this is hosted on the CSE server on a PHP web page, I actually wrote code to call a command line instance of MATLAB and pass in some of this information and run MATLAB scripts to do the interpolation. And the resulting estimated price is then returned to the user, and this will provide them a better idea of the value of their vehicle. So a major application of this would be like if you're looking to trade in your vehicle to a car dealer, you want to make sure that the offer you get isn't a low ball. And so you can use this platform to compare the value of your vehicle against other vehicles that are the same make, model, and year with different mileages, but still have an accurate estimate. And now I can go ahead and go through a live demo. So if you hold on with me for a second, I will go ahead and switch screens. So as I mentioned in the slides, this is the interpolation webpage that we have. So we developed dynamic dropdowns. So this dropdown actually queries all of our data. We put it into a database, and you can select whatever make that you want, and then the model drop down will update with all of the different makes or models for that make. So these are all Honda vehicles. And then the years also update to available years. So one of the things with this data set is that it's large, but there aren't tons of entries for every different type of vehicle make and model. Like as you can see here, there's quite a few. And so we have restricted the years to only allow or to only be available if there's at least 10 different data points. And that is because it's important for our interpolation to be accurate, that there's more than, say, just 1 or 2 data points. Obviously in class, we've learned some of these methods don't work very well. It's hard to do cubic splines on a single data point. It doesn't really work. So we can go up here and select, say, like the Buick, the Encore 4-wheel drive, our available years here. And then we can choose an interpolation method. So maybe we'll do linear least squares, and then we can enter the mileage. Let's say it's got 100,000 miles on it, and we'll calculate. And this does take a while. You have to be patient with it because since all of these calculations are done by querying the live database so that the data can be changed like anytime, it has to load a MATLAB instance, and that takes a while. So I have a tab with that answer to here, so we can see this is what the approximation is with our car doing that interpolation method.
All right, and here we are showing the implementation for our linear least square code. And the bottom left equation shows the math we did in order to, the matrix operations we did in order to obtain the polynomial for linear least squared. Here is our polynomial least squared function, and similarly, we have use a similar matrix operation to obtain the coefficients, although the function is slightly different. And here is our linear piecewise interpolation function.
Yeah, and one thing that I'd like to note about this function is we actually make use of MATLAB sims variables. So you can see right below the line that says create our piecewise, we have sims x. And what's really cool is this function is dynamically building a piecewise function. So in our for loop for each section of our piecewise function, we're actually building that and adding it in. And then we can use subs, this third to last line down there, to actually plug in our mileage as a variable assignment into that equation, then return the expected result.
All right, and then for determining the how well each of these methods perform, we formed a test plan, and our test plan was to pick out a car, a common vehicle, to test these methods on. And our test plan also included to take out a few points from the sample and put them aside as test data, and then we predict we run the interpolation on the remaining data and compare it to the test data to see how well the interpolation predicted the price of the car. So as you can see here, we ran the interpolation for the linear least squared, and on the bottom left we can see the 3 data points we used for comparing. We have the calculated price, which is the estimated price given by the interpolation, and the actual price that came from the data set. And to calculate the error for this instance, for this interpolation method, we find the difference between the actual price and the calculated price, and then we average it. So our average error is the average absolute error between the 3 data points. And here is our interpolation for the polynomial least squared. As you can see, the graph on the right shows a polynomial fitting of the curve to the points. And once again, we use the same exact data points to calculate the error on, so we can compare the methods.
This last graph may look a little confusing. This is comparing the results that we got for linear piecewise interpolation. And one of the things that is challenging with MATLAB is, as I mentioned before, we used those sims functions. And as you can see, we have kind of this stair-step effect between the data points that we're interpolating. And part of the problem with the display is that when you are plotting this function in MATLAB, because it's that X variable is dynamic, it doesn't get assigned when we have this plot. And so what you're seeing is actually the intercepts for each piecewise component between two sections. So we'd actually have connections between each dot on our graph here if we were reflecting what the function looks like when we are interpolating via the website. So that's something I just want to clarify, but we can still see from the bottom left-hand side the calculated prices that we have and the actual price from the data set, which leads us to our average error using the same methods as in the previous two comparisons.
All right, and for providing a recommendation for this, if we were to recommend a interpolation method to be used in an industry setting, we would definitely prioritize linear least squared and polynomial least squared interpolation. We noticed significantly less error when using those interpolation methods when compared to the linear piecewise interpolation. And while our linear least squared interpolation had the least amount of error in this particular test case, we believe that the polynomial least squared interpolation would be better, the better method to use, as we believe it'll generalize for a wider variety of cases.
As far as our conclusions and future considerations go, we'd first like to say that this project would work better with more data. Although we did have a data set of over 1 million records, for some of those very rare vehicles that maybe only 3 or 4 of them exist in the world, they don't get sold very often. If there's not a lot of data points, we're not able to create extremely accurate estimates and predictions for those. So kind of if we had a data set that had more of those rare vehicles in it, that would improve our ability to estimate prices. One of the other kind of common and obvious takeaways is that the outliers can impact the data significantly. This is something that we kind of see with our least squares approximations and our interpolation methods. And lastly, extrapolating beyond the range of the data can lead to a pretty large error. And for some of our functions, such as the piecewise, if you look at the code, you can see that we've actually defined bounds that if the mileage estimate that a user would like to know is lower than our lowest mileage data point or greater than our highest mileage data point, we don't provide an estimate to them because we don't want to give them an idea of what a value should be when we don't have a high confidence of its closeness to the actual value of the vehicle. And if we were to extend the project, some considerations we have is that we would want to have current market data. So someone had brought up this question or point in our class presentation. I thought it's worth noting here that as the time goes on, this data set is all from 2017. And so the value of these vehicles is going to continue to depreciate even if the mileage would not change. And so something that would be a good future addition is to account for that in the way that we approximate the value of the vehicle. And then also building on that, we don't account for the condition of a particular vehicle before we make our interpolation. And so although we do have very, very specific models, so you might have, the 4-wheel drive package versus the 2-wheel drive package, that is something that we separate the data and we can predict the prices better based on those things. But something like hail damage, for example, wouldn't really be covered, or the title state of the vehicle. And those are important to address because they can impact prices. And the last thing that I would also like to touch on that was brought up from a very smart person in our class today too, was that we could also consider calculating the error using root mean squared instead. That's something that in the math community, there's a lot of talk about it being a potentially better metric for estimating error. So that might be something to look into as well. And that will conclude our presentation. So thank you for attending. I will note that as of the time of this recording, the website that we have is running and available on the CSC server. So if you'd like to navigate to csc.unl.edu/tilde/r-lampy, you can access that and play around with it. Thank you.